Welcome to a brief video describing the results of FPath Experiment 008. FPath is my project name for experiments on the Feynman Path to Nanotechnology. And what is the Feynman Path to Nanotechnology? Well, it is the idea that you have large machines make smaller machines, which in turn make smaller machines, and so on until you reach the point where you can reliably move atoms about at the nanometer scale. Of course, the FPath project is nowhere near that yet. It is still operating at the scale of millimeters. This experiment discusses a few commonly available micro-stepper motor-based sliding actuators and performs some experiments to try and get a sense of how much precision one might reasonably expect from them. There are also some image recognition techniques and milliscale closed-loop feedback control demonstrations that you might find interesting. Ideally, for the current stage of the FPath experiments, I would like to be able to repeatedly and reliably position actuators and tools down to about the 50 micron level. So why investigate common off-the-shelf components, also known as COTS components, for this purpose? Certainly, sliding stages accurate down to microns are available, but they are large and expensive. Ideally, I would like to use actuators as small and inexpensive as is possible. Eventually, I will have to dispense with purchased components entirely, but for now, I either need to make them or buy them. I'll leave a discussion of making them for a future experiment. Let's talk about what might be readily obtained. The first actuator I'll discuss is a drive mechanism salvaged from an old laptop DVD player. DVD drives are simple to dismantle and contain a nice sled with some precision rails and a high-ish quality stepper motor. Since the track spacing, or pitch, on a DVD disc is 0.74 microns, one might reasonably expect to rock up some serious precision for free. Well, spoiler alert, no, you don't get that for various reasons, and these will be discussed in due course. The second actuator under test is a stepper motor-driven linear slide commonly available online. These devices are about 40 millimeters in length and are ridiculously cheap. Of course, they are built to a price, and for what they cost, they are actually pretty good. As we shall see, if driven correctly, they can be induced to provide some reasonable precision. For want of a better name, I will call this the large actuator. This one I call the medium actuator. It is about 30 millimeters in length. It too is improbably inexpensive and commonly available. Interestingly, it also incorporates a rail alongside the screw which drives the tool head. This rail greatly simplifies its implementation in experiments, since the tool head is always maintained in a horizontal position, and its presence saves me the trouble of having to mechanically deal with this, something not true in the other actuators other than the DVD sled. The other very interesting feature of this actuator is that the stepper motor drives a small planetary gearbox, which then rotates the screw. The planetary gearbox lowers the gear ratio, which has the effect of giving the drive mechanism much more torque. Of course, it drops the speed as well. You don't get something for nothing. Also, because of the planetary gearbox, there's a great deal more backlash and slop in the drive, which must be dealt with when working with it. This is the smallest commonly available linear actuator I could find. I call this the small actuator, and it is about 15 millimeters in length. Originally, I intended to trial this slide, but have excluded it from the testing for now. To be honest, this device is a total pain to work with. It is very weak and is so small that it is extremely difficult to solder on the 4 wires for the stepper phases. I could make it operate with no tooling attached to the drive head, but as soon as I attached anything to it, it would just stall. I will leave this one for later. I'm sure to find a use for it eventually. It too is very inexpensive. I purchased a small bag of 50 of them for not very much money at all. There are some general considerations to be aware of when using these stepper motors. First of all, you cannot microstep them. The motors simply will not do this. They typically just absorb microsteps without moving until the rotor suddenly snaps to the next position. The reason for this is that they do not have the same internal mechanism as the NEMA-style steppers you might be familiar with. Here is an image of a conventional variable reluctance stepper motor. Although they have 2 phases and 4 wires, they have multiple poles for each phase. This is what makes microstepping practical for them. The variable magnetic field induced on the poles can slowly drag the rotor over the range between the full steps. The stepper motors under consideration here are of the permanent magnet type. They really are quite weak. I assume the trade-off is that it is much easier to turn out small, low-cost versions of these by the tens of thousands. So, when dealing with these motors, always have to keep in mind that they are not strong or of very high precision, and you definitely cannot reliably microstep them. Your mechanical design and software control system needs to take this into account. As some of you know, I like to use Lego blocks as a convenient mounting system on my experimental apparatus. This makes it simple to mount and position the various bits of kit. You can read a lot more about this in the write-up for the Steggo Project. A link is in the description. Here is an example of the DVD sled fully built out with Lego. All that is happening here is that the sled itself is epoxied to a 6x12 Lego plate, and this allows it to be securely positioned on a Lego bed. The movable head of the DVD sled has a 4x4 Lego plate epoxied to it. This allows the moving tool head to change the position of whatever item is fastened to it. A standard microscope calibration slide was fixed to a carefully modified white Lego plate. You can probably see where I'm going with this. The slide carrier can now easily be pressed into place on the tool head of the DVD sled and the whole apparatus move back and forth. The calibration slide has a section with markings of 0.1 mm intervals, 100 micron, and another section with markings at 0.01 mm intervals, or 10 microns. To get a sense of just how small this scale is, here is a video of the point of the smallest sewing needle I could find on top of the 100 micron scale. Here is a view of what it normally looks like. The Microscope is a Mixmart digital USB microscope I purchased some years ago. I don't think it is still available under that name, but is definitely still for sale. I'll talk a bit more about this at the end of the video. You can find a link to a review of this microscope by Dave Jones, that's the Dave Jones of EEVBlog fame, in this video's description. For what it is and what it costs, it is quite a reasonably high quality 2 megapixel USB microscope. The microscope is positioned on the gantry of an old RepRap Mendel 3D printer, and that frame provides a nice, solid, reasonably vibration-free mounting mechanism for both the microscope and the plate containing the DVD sled. The image is received and processed by the Walnut server software. I do not want to go into the Walnut software too much in this video. There are 3 videos describing it in detail. The links are in this video's description. Suffice it to say that the incoming enlarged video stream from the microscope is processed on a Windows 10 PC, and automatic or manual commands can be issued to a microcontroller to move the motor. The other 2 linear actuators also use Lego as a mounting apparatus. Here is a large actuator kitted out with Lego. Because of the limited power of this actuator, I elected to leave the heavy calibration slide carriage placed statically on the DVD sled and mounted a small lightweight arm directly on the large actuator's tool head. This actuator has the power to move the arm. The arm ends with a small flexible bit of plastic scavenged from an old ribbon cable. A black edge has been added to serve as a visible marker when the motor moves it backwards and forwards over the slide. I call this the marker strip. The medium actuator is similarly implemented, and the lightweight arm is also mounted on it for the same reasons. So, enough of the discussion. The linear actuators are placed under the microscope and the actuator is configured to move a certain number of steps. Let's start with the DVD sled. Here is the DVD sled being told to move 10 steps. Note it is the calibration slide that is moving here. The microscope is always stationary. Each division on this display is 100 microns. Interestingly, I've recently updated the Walnut server software to have the ability to overlay horizontal red lines on the screen. This allows on-screen positions to be clearly marked. You cannot see the PC cursor on the current video, but I am just clicking on the display with the mouse in order to place these lines before issuing another move command. If each division here is 100 microns, and each 10-step command moves us about 660 microns, we can easily do the math and work out that each step of the motor is equivalent to 66 microns. Notice the forward and back commands return the grid very close to the original start point. This is quite an agreeable amount of precision. It is the bed that is moving. This is not so for the other 2 actuators. They move the lightweight arm and marker strip described earlier. First, let's have a look at the large actuator. The dark horizontal line across the screen is the magnified edge of the marker strip. We can see that the bed is fixed and the lightweight arm with its marker is being moved backwards and forwards along the calibration scale by the actuator. As before, every division here is 100 microns. Sending a 25-step command, we will see that the actuator moves 265 microns on the calibration scale. This works out to about 10.6 microns per step. The setup for the medium actuator is identical. The tool head moves the arm and marker strip. The medium actuator has considerably finer movements. This is probably due to the usage of the planetary reduction gear. Here I am issuing sequential 100-step move commands and marking each stop position. The distances here are about 280, 240, and 260 microns respectively. This works out to about 2.6 microns per step, which is a rather impressive result for a super cheap actuator. I have confirmed this result by performing numerous repeated tests at various step rates. The trade-off here is the immense amount of slop and backlash observable when changing directions. You cannot see it in this video, but it is roughly 40 to 50 steps. So, let's summarize. The results are quite clear. Cheap linear actuators, commonly available online, can be made to step at a reasonably fine granularity. The DVD sled is not so accurate, but was quite precise and exhibited only minimal backlash. In retrospect, I should have seen this particular result coming. The large thread pitch on the screw of the DVD sled indicates it is built for speed, not accuracy. On a DVD, the fine-grained positioning of the optical read head over the desired track is done by precision electromagnets once the stepper motor has quickly moved the entire mechanism into a reasonably nearby location. Okay, so it seems that the large and medium linear actuators demonstrate some reasonable precision. But, given the backlash involved, is it possible to actually use them to position the tool head? Well, in order to address that question, I set up an experiment on the large and medium actuators using closed-loop feedback control. The basic idea is to use automatic control to move the arm mounted on the linear actuators to a specified position on the calibration slide. We return to the large actuator with the marker strip on the calibration scale. In order to enable the automated control, I implemented an image recognition routine to find the vertical line on the calibration slide and another one to find the edge of the moving part on the marker strip. You can see these as the vertical and horizontal red lines on the screen. These are calculated for each video frame and will move as the display changes. I cause a red dot to appear at the intersection. This is our movable point. And then draw a green dot on the screen by clicking with the mouse. This is the fixed point. If I then activate a move red onto green behavior, left over from experiment 004, a link is in this video's description, we can see the red dot move towards the stationary green dot as the behavior activates the stepper motor to drive the red dot forwards. The red dot moves as the arm moves because the entire arm is being driven by the large actuator. This is all automatic, and once the red dot completely moves onto the green dot, the process stops. I can place another green dot, and the red dot immediately moves there since the move red onto green behavior is still active. It just idles if there are no green dots to move towards. It's kind of fun to drop green dots here and there and see the system track the edge with the red dot onto it. Clearly, the addition of closed-loop feedback provides the system with both considerable accuracy and precision. We can repeat the experiment with the medium actuator. As before, the grid here is 100 microns. The red dot is at the intersection of the horizontal and vertical. I'll turn off the horizontal and vertical red lines put in place by the image recognition system. They just clutter things up. They're still being calculated though, and the red dot will always be at their intersection. If, as before, we drop a green dot and activate the move red onto green behavior, we see a similar effect. Wherever a green dot is dropped, the tool head will move to that position. Note I have been dropping the green dots at the intersection points of the calibration grid. It does not have to be this way. I can drop a green dot anywhere and the system will move the red dot as close as vertically possible. Since that works so well, let's try even higher resolution movement. The divisions here are 10 micron and we are using the medium actuator. This is the absolute maximum of my USB microscope's magnification. The depth of field is not great and so the image is of quite poor quality. Note that at this magnification, the horizontal black line of the marker strip on the arm is very jagged. Because of the coarseness of the image, it is not possible to acquire a clean horizontal line via image recognition. However, just out of interest, let's see if we can get a sense of how consistent the movement can be. Note that the internal squares in the center are 50 microns in size. I mark the edge of the marker strip with a red line by clicking on a reasonable point with the PC mouse. Here I'm using the topmost intersection of the edge with the vertical center of the calibration scale. I then manually set it to move 20 steps. At the previously estimated 2.6 microns per step, we should see the arm move a little over 50 microns. And we do. We mark the stop point and move another 20 steps and mark again. We do this until we get a ladder of 4 sequences. It is looking pretty consistent. As mentioned previously, I've not implemented a move red onto green behavior here because the horizontal line is very rough at this magnification and the tool head bounces about. I believe that better experimental apparatus would probably permit me to move the tool head to a positional accuracy of around 10 to 20 micron resolution when using closed-loop feedback. So, in overall conclusion, I believe that cheap, commonly available stepper-driven linear actuators driven by closed-loop control are a viable positioning solution down to about the 50 micron level. With open-loop control, they aren't sufficiently precise to be usable due to the slop and backlash inherent in their construction. A DVD sled is probably only good down to about 100 microns due to the large thread pitch of the lead screw. However, if one could control the electromagnetic positioning system of the DVD pickup head, I bet that very precise sub-10 micron positioning could be obtained. But that is an experiment for another day. Well, that's enough experimentation for one video. As promised earlier, here is a shot of the Mendel tool carriage with the mounted USB microscope. As you can see, I've stuck a few Lego plates on the top in the thought that it might be useful. A small screw provides a locking mechanism to keep the microscope in place. As you have probably noticed, I'm using a drilled-out Lego minifig head as a knob. Well, what can I say? I guess it's a bit macabre, but I needed a knob and that was a suitable part ready to hand, so I just decided to use it. By way of compensation for the horror of it all, please find in this video's description a link to a really interesting video from the Lego company on how minifigs are made. The bottom of the carriage also has 2 Lego blocks. Using them, I can attach a cheap USB-LED ring light to provide illumination right where I need it. This ring light is quite sophisticated with multiple levels of brightness and color adjustment. The whole thing is mounted on the RepRap Mendel frame, and I can raise and drop the entire carriage to provide gross positioning. I have a small manually operated stepper control module for this purpose. For purposes of documentation, here is the chain of Steggo electronics modules used in this experiment. From left to right, they are a power module, a BeagleBone black breakout module, a small fan-out module to tie the grounds together, a switch to cut off the stepper current without shutting down the stepper motor controller, and a low voltage, 3.3 volts or so, stepper motor driver module. A separate video documents the motivation for using small, separable modules like this for electronics control. As before, a link is in this video's description. Well, that's enough documentation for this experiment. I hope you enjoyed watching, and see you next time.